Hi, I'm Jan Wojciechowski, and it is my pleasure to talk about our work done at Ideas and CBR called Scaling Laws for Fine-Grained Mixture of Experts. The main contributions of our work are introducing a novel hyperparameter called granularity that greatly increases the efficiency of any mixture of experts model, deriving new scaling laws for MOE, the first that allow us to calculate compute optimal parameter to token ratio, and showing that MOE will always be more efficient. Now I'm going to explain how granularity works. In the standard MOE setting, each token is assigned to one or k experts of the same size as the regular feed-forward layer in the base transformer. Such a model has granularity 1. Introducing granularity 2 to the model means that we split each expert in half and route each token to 2 times more experts. In this way, we keep the number of activated parameters and total parameters inside experts constant. We can define granularity as the number of neurons inside the base feed-forward layer divided by the size of the actual expert in our MOE. Granularity gives the model more flexibility as it can emulate regular MOE, therefore intuitively it should be better. In our preliminary results, we have seen that just increasing granularity leads to greatly improved performance. Here we can see on a plot how the same model with exponentially increasing granularity converges. However, this is not the correct way to compare these models. Normally, the routing cost in MOE is considered negligible, but in our case, it increases linearly with granularity. So for a fair comparison, we have to take it into account. These trade-offs can be solved with scaling laws. For example, chinchilla scaling laws predicts loss using 2 hyperparameters, number of training tokens and number of model parameters, and we can use it to calculate compute optimal parameter to token ratio. There also have been created scaling laws for MOE models that derive the function that predicts loss using the number of parameters and number of experts. However, they do not consider variable training length, and all the experiments share the same datasets. Therefore, it does not allow them to calculate the compute optimal parameter to token ratio for MOE models. Extrapolating over the number of parameters while keeping the dataset constant, they've predicted that regular dense transformers will surpass MOE at effectiveness after we scale up to 1T parameter models. In our scaling laws, we study the relationship between 3 hyperparameters: number of training tokens, number of parameters, and granularity. We have observed the power law governing how granularity affects model's performance. Moreover, we have observed that granular MOE also obey chinchilla scaling formula, just with different coefficients that depend on chosen granularity. In our work, we derived a joint formula that is consistent with both observations above and is visible at the bottom of the slide. Then we ran over 150 experiments on models with up to 3.7 billion parameters to fit the coefficients. To verify our results, we have excluded top 20% of the best models from our training set and used them as a validation for our scaling laws extrapolation. This plot shows the compute optimal curves for MOE models. Colors indicate regions in a curve where corresponding granularity is compute optimal. We can see here that as we scale up the model, granularity should increase and relatively high granularities are compute optimal even for smaller models. For example, 16 is optimal for models of 1B active parameters. However, we have noticed that MOE performs worse at the beginning of the training. This explains the result of the previous work. When scaling only the number of parameters, we will eventually enter the regime where the model is severely undertrained, and in this uncommon scenario, MOE is actually worse. However, when both models are trained in a compute optimal manner, we can see that the gap between MOE and dense transformer only widens as we scale. This plot shows how many more flops do you need to train respectively regular MOE and regular transformer to match the performance of granular MOE. We can see here that granularity saves around half of the flops, while MOE alone saves around 10 times. So to conclude, the standard value of granularity 1 is never optimal. Granularity should increase as we scale, and MOE will always be more efficient. Thank you for your attention. This was Jan Wojciechowski talking about scaling laws for fine-grained mixture of experts.